Okay, it is 1 minute past 6 or 1 minute past some time. So we'll get started. Thank you everyone for coming to the penultimate colloquium of the year. We are very pleased today to have our own Evan Patterson talking about categories of diagrams in data migration and computational physics. So Evan, please, whenever you're ready. I'm sorry, just to clarify, your question policy is that you're happy to take questions during your talk, yes?
Yes, I'll take questions as I go. If for some reason it seems too long or complicated, I'll push it up to the end, but I'll try to answer questions as I go. And I won't be very good at looking at the chat, so maybe Tim, maybe David, you can interrupt me if I'm not seeing something. Okay, great. Yeah, so this talk, I'm going to talk about the interesting categories that one gets by looking at morphisms between diagrams in a particular category. And this will be a fairly sort of application focused talk. So the main thing I want to do is illustrate how this set of concepts appears in two different applications that I and my collaborators have been working on recently. So one is sort of data migration stuff in categorical databases, and the other is a project, quite different flavor of project related to computational physics. So I think it's sort of interesting that we'll see some of the same concepts appear in these quite different settings. So to get started, I'm just going to talk about what are some of the basic notions here. This won't take too long, and then we'll get to sort of the applications. So if you like category theory at all, you know what a diagram is. And so this slide is mainly just to sort of fix notation and remind us all of what we're talking about. So let's remember that a diagram in a category is a functor into that category, where the domain of the functor is usually assumed to be a small category. It's called the shape or the indexing category of the diagram. And there are a couple common classes of diagrams that one encounters. So a free diagram is one where the diagram shape is a category that's freely generated by a graph. And a lot of the diagrams that one encounters out there are actually free. So all of the ones in this talk will be, and that's sort of convenient computationally because it's easier to work with a graph than a general category, certainly. And then a commutative diagram is a free diagram where the images of any two paths in that domain graph that have the same source and target get mapped to equal morphisms in C, right? So to be super concrete about what we're talking about, one kind of diagram, it would be a span. And then now I hear the siren going off outside. Sorry about that. So the indexing category would just be the graph that has two distinct arrows emanating from some vertex, and then the assignments or whatever you need to have to get the span that you want. Okay, so we all know and love diagrams, but what I think is a bit less well known, or I didn't really appreciate this until pretty recently, and I think that maybe not everyone has thought about this too much, is that having fixed a category C, the diagrams in that category have several different natural notions of morphism between them. So if you pick one of these, you'll get a category, and actually there's even a good notion of two morphisms, so you have a two category, but in this talk we'll just be sticking to the one categorical structure of this, even though it's really properly understood as a two categorical notion. So I learned about this from two recent papers by Walter Tholen and his collaborators. Another author in one of these papers, Paulo Perón, spoke just last week, I think. So these papers emphasize the role that diagrams play in the decomposition of colimits, and we'll see that these morphisms of diagrams are, depending on how you choose them, are closely related to limits and colimits. And then So these were recent papers, but this notion goes back quite a ways. So there was a number of papers in the 70s by René Guttard, probably not pronouncing that right. These papers are mainly written in French. But the basic notions here go all the way back almost to the beginning. So the first work, I think, to study the fact that there's actually a monad on this category of diagrams was Anders Koch's PhD thesis, and then actually the basic definitions are buried in Eilenberg and MacLean's original paper. So it goes all the way back there, and it took quite a bit of digging though to eventually realize that's a bit fun. But what are we even talking about? Okay, so there are several different conventions for what the diagrams can be depending on what you're doing. So the most obvious one is to take the category diag C to have as objects diagrams in C, and then a morphism from a diagram D to a diagram D prime, which generally has a different shape, is going to consist of a functor between the indexing categories, and then as well as a two-cell between, forming this triangle. So, and then there's another category which I'll call diagram op of C. So I'm putting the op before the parentheses to try to, this is not a good notation, but to try to emphasize that, like, I'm not opping the whole category, I'm just opping the one cell part of this morphism. So the functor between shapes is now going in the other direction, but the two cell goes in the same direction as before. So, and some people might reverse the convention, but okay. So these will be the basic sort of things that we'll be looking at, and we'll see that you can do some neat things with them. Okay, so in the first part of this talk, I'm going to talk about the role played by diagrams in functorial data migration. And so this part of the talk is in collaboration with my colleague here at Topos, David Spivak. So, so many of you have probably heard a bit about the categorical databases or functorial data migration story, but let me sort of remind you what this is about. So the point of departure for this story is that, relational databases can be modeled in a very simple and elegant way using nothing but the most elementary concepts of category theory. And this model that I'll describe can be elaborated in various ways, and it can be useful to elaborate it if one wants to accommodate, practical features of real database systems. But for the purposes of this talk, this very simple model is enough. So, so according to this dictionary, a database schema is just a small category C. And so usually this would be given by, you finitely present this category, introduce some objects which represent, tables, entities, and you introduce some morphisms which represent, foreign keys between tables or columns. And having defined your schema, you can look at a database instance, which is a co-presheaf on C, or a C set, which is just a set valued functor on C. And then finally, a homomorphism between database instances is a natural transformation. Okay, so I have here below everyone's favorite, very simple but nevertheless useful example of a schema, which would be the schema for graphs. So this is just two parallel arrows, and the objects conventionally labeled like E and V for edges and vertices. This is a directed multigraph with loops. Okay, and so having adopted this categorical viewpoint on databases, it suggests sort of this idea of functorial data migration, which was the topic of David's first paper on this topic, I think, or one of the early ones. And the basic idea here is that if you have a functor between your schemas, this should somehow induce a functor between database instances on those schemas. And the simplest way to set this up, the starting point for this is to consider the pullback data migration, whereas this is a contravariant form of data migration. So if I give you a functor from D to C, then the precomposition with that functor defines another functor from C sets to D sets, right? And so this is depicted by the picture here. And so there's a limit to what you can express with this. Nevertheless, it's useful already for defining some things. I like to think it's useful for constructing like forgetful type maps or other things, that projections, things like that. So to give an example of what you could express already with this, you could say, well, the schema on the bottom right here is the schema for directed port graphs. So now we're calling the edges wires and the boxes, the vertices boxes, and we're saying that every box has a set of input and output ports, and wires go from output ports to input ports. And we can think that every port graph has an underlying graph that's given by forgetting about the ports. And this transformation can be expressed using a pullback data migration, where the mapping is maybe clear from the picture, but is also sort of depicted in sort of the code interface that one could use in Catlab on the left. So it's clear, but like the source edge in the graph schema goes to the composite of source with the box that the output port is associated with. Similarly for target. Okay, so it's always true that given one of these pullback data migrations, there are left and right adjoints to that functor, and they're useful for, and these are quite powerful, and they're useful for various things. For instance, the left push forward is useful for doing free constructions, like give me the free symmetric graph on a graph or something like that. But there are some real challenges with this approach. So one is that in general, computing these adjoints can be quite difficult. So there's a paper by Spivak and Wisniewski that goes into quite a bit of detail about how to compute some of these things in different cases and some of the challenges involved. Also, the databases that one is supposed to get can sometimes be infinite. So that's a real practical problem, because certainly SQL databases don't hold infinite data. And then there's also sort of a challenge of more like a usability challenge of like, it's hard even for people who know about this stuff to sort of anticipate what these things are going to do. That can be a bit hard to think it through unless you're very experienced with working with it. And so for a combination of these reasons, in this talk, I'm going to consider sort of a different approach, which is rather than looking at the adjoints to the pullback, instead we're going to stick with this contravariant form of data migration, but we're going to try to boost its expressivity. And so the result of this will be that the system that I described here is like less automated in a sense. It's like less magic, but it's also more explicit, and it's easier to understand. And as far as I'm concerned, it's also easier to implement. Okay, so how are we going to do this? Well, we can do a kind of just a little formal calculation here where we ignore maybe size problems and stuff like that. And thinking about this, we can just say that using like the Cartesian closed property, we can rearrange what a functor from C set to D set is to say that, well, to give one of those things, what I need to do is I need to give a functor from D to the category of set valued functors on C sets. And that thing, I think of it like conceptually as like it's all the possible queries one could do on a C set. Like I give you a C set and you give me a set back, and like that's the result of a query. Now, this is not really a viable set of things to look at. It's sort of too big in every sense. And so what we're going to do instead is try to restrict to tractable classes of queries. And so the most natural thing to start with would be to say, well, we can look at the representables in here. And so in other words, that corresponds to fixing some C set Q, and then looking at the functor from C set to set given by, the Hom set of things out of Q. And turns out that these correspond to what are in database jargon called conjunctive queries. This is like the most kind of fundamental notion of query that every relational database system supports. And in this jargon, the C set Q is sometimes called the frozen instance that corresponds to the query. And so you might say, okay, well, that's good. Are we done? We're not done, because there's a further difficulty, which is that even this object Q could be given, let's say that it's like a finite colimit of representables. Well, it could still, if some of those representables are infinite, it could still be that Q is actually an infinite object. And so again, we don't want to construct and work with that thing. We want to have we want to have like a finitary way of describing these queries. And so what we're then going to do is we're going to replace this category of conjunctive queries, which if you think about like the Yoneda embedding here, this is C set op. We're going to replace it with something more syntactical, and that thing is going to be a one of these categories of diagrams, which I introduced at the beginning of the talk. So, but which one should we use? And so this brings us to sort of one of the fundamental properties of these things, and one of the strongest motivations for them. And this is actually why Eilenberg and McLean introduced this in their paper. So, so the fact is that if you looking at diagrams in some complete category S, which for us is just going to be set, but take anyone stating this theorem, then the operation of taking limits gives a functor from diag op S to S. So on objects, you take the limits, and then the point is that these morphisms give you a way to construct morphisms between the limit objects. So I'll explain briefly how that goes in a second, but then the dual statement is that if S is a co-complete category, then this other category of diagrams, the covariant one, turns colim into a functor. Okay, well, so let me just kind of, it's actually fairly intuitive what to do here. So like how would you actually operationalize this first statement about diagram op and limits? So in order to give a map into like the limit of d prime, I need to give a cone over d prime. And so how do I do that? Well, I can start with the limit of d. So okay, so for every j prime in the shape of d prime, I need to pick some j in the domain shape, and then I project out of the limit of d, and then after that I'm allowed to hit it with the result. I'm allowed to hit it with the corresponding component of this natural transformation. And you can check that like the naturality condition is what gives you a cone, and so this works. So this is like what you can do, and we'll see some examples of how you actually use this in practice. Once you get used to it, it's fairly intuitive. So then we'll say, okay, that then a conjunctive data migration will be a functor from C set to D set that's defined by a functor of this form from D to diag op of C. So to be very explicit, what this is saying is that to every object in D, I'm going to assign a diagram in C, and I'm going to interpret that as a limit or as a conjunctive query. And every morphism in D is assigned a morphism of diagrams in C in a compatible way. And then based on the ingredients that I've introduced, it's quite simple to describe how one actually evaluates one of these queries. So if I give you a C set X, what do? I start with the definition. I start with the schema for this migration, which is this functor F, and then I post compose with X to get a functor from D into diagrams and set, and then I hit it with the limit functor, which I just described, and that gives me a set. And so the composite of this whole thing is a functor from D to set, or D set. Okay, so let's see a simple example of how you can do with this. So if you wanted to take the graph and return a new graph that has the same that has the same vertices and whose new edges are the paths of length 2 in your original graph, you could do it with this sort of migration. Say I'm going to map V to V, and then I'm going to map E to this. This is specifying this syntax is specifying the diagram, which is shown on the bottom here. And then what do you do with morphisms? Let's walk through this. So to give a map from the diagram at E to the diagram at V, I need to give the shape map. Well, the diagram at V is a singleton. So all I need to do is pick out a single object here in the diagram at E. So I'll pick out E1, and then I'm allowed to and then I also need to specify the component of the natural transformation at that point. So I'm allowed to do something with this edge. Well, so this is the first edge in the path. This is the second one in the path. So I can pull out the source of that edge, and so this line is defining both that R at that point and the component of rho at that object. Okay, and so hopefully it's sort of intuitively clear what that's doing, and that makes sense. Okay, but now we're really just getting started, right? So now that we sort of understand the basic way this works, we can really turn the crank on this and get a lot of different kinds of queries. So by dualizing, we can get what I'm calling gluing queries. It's not a standard term. I don't know that there is one. So these are what you get by using colimits instead of limits. And then we can also start to put these things together. So we get this sort of hierarchy of queries that generally sort of increase in expressivity. So from one point of view, we can think that C itself just represents the trivial queries, so that and then we've seen that the conjunctive queries, or I've guessed that the conjunctive queries correspond to diagram op of C. If we just want disjoint unions or coproducts, we can take the full category of diag C that's spanned by the discrete diagrams, and then combining those two things gives a nice class of queries called disjoint unions of conjunctive queries, or David likes to call these duck queries. So that would be in this category, which I'm calling bundles of diag op C. And then we can really go, sort of all the way here and say that, okay, we can also have gluing queries, and finally we can have what I'm calling glut queries, for lack of a better term, where every query is sort of a colimit of a limit. So it's like quite expressive. Now, in practice, to have to maintain some kind of reasonably manageable syntax, we have to be able to kind of implicitly convert between these different query classes. And so the convention that we use is that, you can, given an object in C, you can regard that as either a gluing query or a conjunctive query just by taking it to be a singleton diagram. And so as the notation suggests here, this is the unit part of some monad on this diagram construction. And then we can sort of apply that again to get to glut queries. And so the convention here is that you put the colimit on the outside. Okay, so let's see some examples of like how this works. So to upgrade the previous example a bit, you could say, well, what if I want instead the graph whose edges are paths of length at most 2? You could say, well, I can use a duck query to do this. So this is a duck data migration, where for the edges, I'll allow it to have, the edges will basically be the coproduct of the vertices, the edges, and the paths of length 2. And then to give the morphism, I have to give sort of a morphism between diagrams of the appropriate kind, which sounds cumbersome, but it can kind of be reduced to a fairly simple specification here. So like, that's what's shown below. I won't spend too much time on this. I'll post these slides later, so if you want to look at these examples more, you can. And so here's, I want to illustrate why you might want to use one of these gluing data migrations. So this example is a bit more advanced. I won't spend a lot of time on it, but the basic idea here is that if, let's say you want to construct the free symmetric reflexive graph on a reflexive graph. So in other words, I want to freely add edges in the opposite direction. So because of the reflexive loops in the original graph, so normally what you would do, so to construct the free symmetric graph on a graph, you just add an edge going in the opposite direction for every edge in your original graph. But in this case, if we just do that, we'll end up with 2 copies of the reflexive loop. And so you actually need to do a bit more. You then need to glue the edges that correspond to the reflexive loops together. So that's what's done here. That's what's done with this colimit. And then you can set up the morphisms accordingly. And in this case, we need to give the, we're giving the morphisms associated with this colimit names because we also have to map them to each other. Although in principle, maybe a future version of the system would be able to infer what those assignments have to be and reduce some of the code required.
So Evan, can I ask a question? So these examples run currently in Catlab?
Yes, I'm getting to that, but yes, they all run.
Oh, okay, sorry.
They all run. Yeah, so it's not, right, so I'll describe that in a little bit here. So I'm summarizing here and I'll talk about that. So the advantage, as I see it, of this form of data migration over, say, like queries on a SQL database are twofold. So first, like, and this applies to all forms of Functorial data migration, not just this one. Like SQL queries, they take a database and give you back a table, but then having gotten the table, you've sort of like left the relational framework, and so you can't say compose queries in any straightforward way. So the nice conceptual thing about data migration is it takes you from a database to a database. So one can think about composing queries, one remains in the same world after that you started in after doing a query, which is very nice. And then in this approach, we also get a class of queries which is significantly more general than like I've never heard of a relational database that will basically can do like general kind of colimits. And even the support for unions in SQL databases is a little questionable. I mean, it's there, but it's a bit awkward because of the table-centric viewpoint. Okay, so to summarize, this entire talk I've kind of illustrated how diagrams can be used as a combinatorial syntax for queries, and then how the morphisms of diagrams let you specify then if you want to do a data migration, what will be the foreign key relations between the results of those queries. Yeah, and to answer David's question, so all of this is implemented in Catlab. There's a prototype implementation. So all the examples shown here work, and it relies on pretty significant past investment in Catlab on having good, reasonably good algorithms for evaluating limits and colimits and set. So we've got this big machine that reduces things to computing limits and colimits and set, and then puts it all back together. And so hope to have a blog post out at the end of the year with a bit more about kind of on the software and programming side of what's going on there. So some future things that I'd like to work on in this space are, certain classes of these queries can be composed using the monad structure that these things have, and as well as a distributive law. Also, on a practical note, I'd like to do kind of more flexible specifications for transformations of data attributes, so being able to use like arbitrary Julia functions involved in that data transformation. And also, David just put out a new work about doing group by and aggregation type things, and so I'm interested in how those sorts of ideas can be accommodated into this. So ultimately, for me, I've sort of focused on some of the category theoretic underpinnings of this, but for me, this is a practical project. What I want to do is build the most expressive kinds of relational querying and data migration capabilities that I can. That's the goal. Okay, so that's part one. Maybe I will pause for a sec to see if there's any short questions. And then I'll go on to the next part. Okay. So if you got a bit lost there for whatever reason, now is a good time to check back in because we're changing gears. So I'm going to talk about a project that's been going on for over a year now in collaboration with a number of people, James Fairbanks at University of Florida, Andrew Boss, Jesus Arias, and Maya Gatlin, all at the Georgia Tech Research Institute. And this summer, we were also lucky to be joined by Sophie Lipkind and Owen Lynch, who are grad students at Stanford and Utrecht University. So this has been a good size project, and I won't be able to do justice to all the great work that the people have done here. I'm just going to focus on sort of a piece of this project, and hopefully we'll have other occasions to say more about other things later. So the overall goal of this project was to develop compositional methods in software that would reduce what is now the very substantial engineering effort required to build physics simulators, by which I really mean PDE solvers, numerical PDE solvers, that includes situations where you might be wanting to use physics that go beyond what's available in like a standard solver. So like the certain very classic equations have dedicated solvers that are very good, very specialized. But what if you want to start combining different physical theories in a new way, you know, do you have to go off and write your whole solver from scratch, or can we somehow have a more generic approach? And then we also want to be able to allow for the possibility of having these physics being on complex, you know, geometries. I mean, I don't know exactly how my colleagues see it, but I see this project as having a couple different sort of areas. So one of them is sort of really very category theoretic in nature, and it's about sort of a diagrammatic formalism for how you can specify and compose physical theories. And this is sort of loosely inspired by this thing called Tonti diagrams. There's like sort of a differential geometric piece, which has to do with like, well, what are the spaces, the geometric spaces and the differential operators involved in specifying these equations? How do you discretize them? So the approach we're using here is something called the discrete exterior calculus, and we have an implementation of that available now. And finally, there's like the numerical aspect of it, which is like, okay, well, how do you put this stuff together to actually make a real solver? And we've got some solvers at the prototype stage, and we'll also be releasing software for those soon. So there's a ton here. I'm just going to try to focus on a small slice of this, just to sort of give this first part of it, just to sort of give a flavor for how the diagrammatic stuff appears here. Okay, so there's this thing called Tonti diagrams, and they are a loose family of diagrams that are used to depict the quantities and differential equations that you know constitute like sort of physical theories. And they were promoted and popularized by this fellow named Enzo Tonti, which is why they're called Tonti diagrams. But there's a lot of variations of these things that appear in the literature, and they're not always called Tonti diagrams. But so like here's one which is supposed to be showing like just Newton's second law, and the classic, let me skip this one. The classic starting point for all this stuff is the way that Maxwell's equations appear in the exterior calculus is like has this kind of very, you know, there's all these different spaces involved, and so it's natural to start to draw these pictures. And so people have draw this picture, which some people call Maxwell's house, which shows all the quantities sort of laid out in this fairly regular looking way. So this is some very busy looking version of Tonti's house. This is, I'm sorry, Maxwell's house. This is another one. Here's yet another one by a different author. Here's someone else drawing a similar diagram, but with a much less appealing layout, but similar diagram, it turns out. Okay, and then and Tanti has really tried to like push this diagrammatic presentation to great length. So here he is trying to do the NavierStokes equations in some kind of diagrammatic form, and here we start to see some maybe challenges of how far one can take this approach. There are some various things going on in this diagram that it's hard to know exactly what it is, and so you know a basic. So kind of one of the things that we're trying to do here is just can we put these diagrams on some kind of rigorous footing and understand, you know, what the heck are these things. So if you've been paying attention at all in the talk, maybe you're thinking, oh, well, you know, are these diagrams, are they just going to be kind of category theoretic diagrams in some sense? And I think, you know, the starting point of an answer is that almost, but what they really are is like they're describing a kind of a lifting problem, which is associated with a diagram. So to explain this, we're going to take our diagrams to be in some category C, and the interpretation of this category will be that the objects of C are going to be the are spaces of physical quantities. So think of things like scalar fields, vector fields, differential forms, that kind of stuff. And then the morphisms will be, differential operators between those things. So, like the exterior derivative, or if you're in vector calculus, like the gradient, that sort of thing. Okay. And for present purposes, I will not say precisely what this is, because it's not that relevant to the general discussion. So a minimalistic choice for what C could be would just be the category of real vector spaces, in a sense that all the categories that we might consider are going to have like forgetful functors to that. But more structure is present here, and depending on whether you're working in the smooth or discrete exterior calculus, you might want to set it up in different ways. Okay. Okay, so we're going to be looking at diagrams not just in C, but also in a category of generalized elements of C. So we're going to fix some object U in C, which is the one that we're going to use to probe C. So, if C is vect, the most obvious thing to do would just be to take U to be the one-dimensional vector space, so that, maps out of U are just vectors. And we'll write L of C for the co-slice category associated with this. So to remind you, this just the objects of this are morphisms out of U, and the morphisms between such things are commuting triangles. And so we're going to kind of write this morphism U to X in this sort of suggestive kind of type theory looking notation of like little x's of type big X, and that's sort of the intuition. And so then the basic idea is to say, okay, well, we're going to think about a diagram in C as being a system of equations, and then a diagram in L of C, in this category of generalized elements, is then going to represent some kind of solution to a system of equations. So let me try to spell that out a bit in a bit more careful way. So what we're really saying is that we're going to look at, associated with a diagram in C, a lifting problem, which is to say we're going to look for a diagram D bar in L of C that projects back down to the diagram we started with. And if you think about how if you unwind what these definitions are saying, what this is really saying, an equivalent way to say this is that the lifting problem is to find a cone over D with apex U. So there are a lot of different ways to describe the things I'll be talking about. So depending on what it can be useful to have different ways to say the same thing. But so thinking of it as a cone sort of illustrates that there's a connection here maybe to limits. And I'm not going to say too much about this, but that sort of makes sense, because if we think, like, a good intuition is that limits are about finding solutions to equations, whereas colimits are about like imposing solutions on equations. And so, when we solve a PDE, we don't want to change the PDE, we want to find solutions to the PDE in any event. Okay, so I think an example will maybe help kind of bring this out a bit. So and if you don't know, if you're not familiar with exterior calculus, some of this might just seem like a bunch of weird symbols. But the point is that this is a diagrammatic way to present the diffusion equation in the exterior calculus. So on the one hand, so this C is supposed to be the concentration of the diffusing substance. It's a zero form, or just a function on some manifold M, which we've fixed. Here we're assuming a three-dimensional setup. And so there we have this diagram which says, on the one hand, you can go from C to C dot by taking the time derivative. And so that gives one side of the equation, but you can also, follow this path here where I apply the exterior derivative, the Hodge star up to this diffusivity constant to get something called phi, which turns out is like the negative diffusion flux. And then I can do another exterior derivative at inverse Hodge star. And so this other path this other path is basically the Laplacian. Okay, so the point, there's a subtle point here, which is that like the diagram that I'm showing, first of all, I'm using this diagram. This diagram is drawn as a diagram in L of C, but this is like the same way as when you write down a differential equation. If you just look at the equation, it's not clear whether the notation represents a particular solution that satisfies it or like the thing that you want to solve. So here what I'm saying is like, this is representing a thing that I want to solve. So this is, but the point is that the diagram in C, or if I find a lift to LFC, all of these diagrams are free diagrams. They don't commute. What is making this work is that like, if I have a lift of this diagram, then what that's saying is that if I apply these operators to that particular element as I go around these paths, I get the same thing. But the paths don't commute in general. The whole point of solving the equations is to find something for which they agree. So now let's bring in the diagrammorphisms. So if from the first part of the talk and the connection to limits, we should perhaps have the idea that the right notion of diagrams here are diagram op, because these are the ones that play nicely with limits. And so we're going to see, depending on time, either probably just one use here, which is to express boundary conditions and help formalize boundary value problems is a more general kind of lifting problem, which I'll call an extension lifting problem, although the diagrams can also be used kind of in a more general way just to construct kind of like formal relationships between different presentations of physical theories. Okay, so let's see how we can use one of these diagrammorphisms to attach some boundary conditions to this thing. So let's say that our system is a diagram in C, D, and then a morphism into some other diagram D naught can be used to describe boundary conditions. So here's the diffusion equation. I'm going to attach Dirichlet conditions to it. So in other words, I need to specify two things. I need to specify the initial condition, so the concentration at time t equals 0, and the boundary conditions, which is the value of C on the boundary of the manifold at all times. And so to do this, I can take this category D to just be a discrete diagram, and so both of these C naught and CB, the objects in the indexing category map to the one that corresponds to C, and then indicated in dotted lines here are the components of the natural transformation. And these are the restriction maps. So okay, so this whole picture illustrates in a somewhat not perfectly precise way a diagrammorphism. Okay, so this is probably the last thing that I'll get to, but I at least want to kind of explain the idea here. So we can then say, so when you solve a PDE, you have the PDE and you have the boundary equations, and you need to find something that satisfies both. Okay, and so we can describe this by extending from just like a lifting problem to an extension lifting problem. So if I have a morphism in diagrams D to D naught, which represents the boundary value problem, and then let's say I also have some data, so this would be a lift of D naught, then the goal is to find a lift of this morphism of diagrams that projects back down to my original one. So in other words, I need to find a D bar that is a lift of D through the projection. So that's solving the equations. And then simultaneously, I need to extend the data at D naught bar to D bar through this map R, and I need to extend it up to this natural transformation, and doing that is satisfying the boundary conditions. And so problems like this appear a lot in sort of topology and subjects like that, but so this is sort of, but in a geometric setting, this is sort of like the diagrammatic analog of a problem like this. And let me just, I'm going to kind of conclude here. So I've only sort of begun, so in a way we've sort of just got to the meat of this. So there's a lot more to discuss along the lines of this formalism. So, looking at, we can look at what kind of morphisms of diagrams actually give you sort of equivalent diagrams, in the sense that they have the same lifts or the same solutions, and that leads to looking at something called initial functors. And a relevant work here is the paper by Street and Walters on what they call the comprehensive factorization. On a much more practical note, there's we can compose, you can build up diagrams from smaller ones using structured cospans, and this is pretty easy when you have free diagrams to kind of make this work. And the other major direction is that in order to express more equations, things going beyond, very simple ones like the diffusion equation or the wave equation, we need to add some more stuff to this formalism. So we need to allow ourselves to have Cartesian products and or general monoidal products, depending on situation, in the diagrams, and there's sort of a story there. But when you've worked that out, you can really start to do all the major equations of mathematical physics. So you can write down Maxwell's equations and the NavierStokes equations and stuff. Okay, so, and of course, I also, as I mentioned, I haven't discussed sort of the whole computational pipeline associated with this, which is that these diagrams also, like the connectivity of the diagram, by traversing that, you can like create a computation graph, like which we represent as a wiring diagram for what you need to compute in the vector field for the discretized system, and then you can we can turn that into a numerical simulation running in Julia. And so there's a fair amount going on there. I haven't done justice to it all. But since we've come this far, I do want to, as one last thing, I do want to at least show you that we, although we like category theory, we also do like solving equations too. So I'm going to show this a numerical example here. So this is results from one of our simulations. So this is Maxwell's equations, where we have set up some initial, maybe it's a radial distribution of for the E and B fields, and then we're just letting them freely propagate in this box, which has like a perfectly reflecting boundary. So you can sort of see this wave-like kind of behavior and propagation. Okay, so that was a lot at the end. I went kind of fast there, but hopefully you're still able to take away some things, and I'll stop there and take questions.
Thanks, Evan. Great talk. So lots of people are clapping in the thingy. So anyone who wants to unmute and ask a question, you're free to do so. If you want to raise your hand instead, I'm happy to call on people. I had a question while we're waiting.
Yeah.
Your extension lifting stuff that you use to do boundary value problems, does that have a database correlate? Does it mean something from the CSET perspective?
Yeah, it's funny you ask, because maybe I should have mentioned this, but the place I actually got the inspiration for that from was from your paper on basically database queries as like lifting problems. And there's so there are, I think in that paper you just called them lifting problems, but they're extension lifting problems in the jargon I was using, but just in a different sort of setting. So like there's formally some similarities, although I don't know like like a precise answer for what the connections are, but there's maybe some interesting connections there. So
okay, well, thanks. I'll go take a look at that.
Yeah.
I think we have a question from Michael. Feel free to unmute and ask. There's also a question from Michael in the chat, which I could read if Michael doesn't.
Sure.
They ask, do you have any reference for diagrams with monoidal products?
So I can just sort of explain. So eventually hopefully within the next few months, we're going to write a paper, we'll have a paper out about this stuff. And that will be something to look at, but I can explain sort of the basic approaches to extending this. So if you just want to do Cartesian products, the simple thing to do is to basically, depending on how you look at it, it's like moving from cat to Cartesian cat, or you can think of it in a more syntactic way and as maybe something closer to like finite product sketches. But the way I think about it is just like where instead of looking at diagrams in cat, we're looking at diagrams in the category of Cartesian categories. And so in practice, what that means is that you have product objects and you have projections out of them. And then you can encode equations, because like, in the lifted thing, like a product becomes just like a tuple of elements, and the projections tell you what are the components of that tuple. And so then you don't really have to change. You can still work in this very sort of diagrammatic setup without changing a whole lot. If you want to do general monoidal products, maybe there's other ways to think about this, but what I'm currently suggesting is that because these are all free diagrams, we don't actually need to illustrate commutation relationships in the diagram, and so therefore we're free to use other kinds. So in other words, let me try this again. So like we can move from cat to like SMC, and then we can use the fact that like something like a Petri net is what presents a free SMC. And so we can basically draw like Petri net style diagrams to incorporate monoidal products. So those are some of the things that you can do while remaining in this general sort of setup.
Oh, Michael, we're not hearing you.
Yeah.
We see that you're unmuted, but we also can't hear you. Sorry about that. Yeah, maybe you can type it in the chat and I'll read it out. But if anybody else has questions in the meantime. Are you looking at the chat, Evan?
Oh, good chat.
So So Michael says it would be great to read
Oh,
the paper.
yeah. So I have a fair amount of typed up notes, but they're not really suitable for distribution. But within a couple months, we should have something. So yeah.
And I could run that Maxwell's equation in the box thing in Catlab right now.
You need some other, yeah. So Catlab plus other software. So you need Catlab. You need this combinatorial spaces thing, which basically contains an implementation of the two-dimensional discrete exterior calculus on simplicial complexes. We use like semi-simplicial sets. And then you also need the thing that sort of integrates all this stuff together, which is the software that is in sort of a alpha stage, but which is it is available, but is not quite ready for prime time. But it'll be. I can put links to that someplace once it's a bit more ready. But yeah, so you need a couple different components, but the stuff it's all open source software. Yeah.
And the overarching ecosystem is algebraic Julia, is that
That's
right?
Right.
Okay. Looks like Michael is asking another question. So due to problems with categories with multiple canonical notions of monoidal products that need to disentangle.
Yeah, so, okay. Hopefully this is the right interpretation of the question. Like, so what do you do? So this is indeed a very common problem in like applications. Like you've got, say, like vect, it has two monoidal products. It has the direct sum and the tensor product, and you need both because like the like the Lie derivative operators like that are they live, they make sense with respect to the tensor product. But if you want to do something as basic as addition, you need the direct sum. So what do you do? There are two approaches that I know of, and with their pros and cons. So one is to one would be to use this Petrinet style thing for the tensor product, and then just use the Cartesian product in there with the same device that you use it in like the that I was describing earlier. And the other approach, which might seem weird, if you're a mathematician used to always thinking that like the morphisms in vector linear maps. The other option though, which is in some ways simpler, is to say that, okay, we're actually going to move to a category where we allow ourselves to have nonlinear maps. And then we only need one then we don't need a tensor product, because the only reason the tensor product exists is to like turn multilinear things into linear things. And so we can just have the Cartesian product, and then we can encode like multilinearity type equations just as additional equations that hold, but we're not going to insist that they hold for all morphisms. And so that gives one way where you can stay in sort of the classic diagrams just using the Cartesian product, and not have to get into the tensor product at all. Although, as I said, if it might feel a bit weird if you're used to thinking everything should live in vector.
Cool. Well, let's stop it here and thank Evan again. So thanks. This was great. We'll end the live stream, and anybody who wants to stay on